even when it just moves down. And if it's moving left and right. I mean left or right. So I want to draw it on the last iteration. Not on the last iteration no matter what, but I want to draw it if it moves. Which it's not, well, it is going to move on the last iteration, I guess. But if, okay. If B, okay, so basically what I need to do is I need to give it an option. So I need to do it here. I need to do it like here. There's two things. There's either B is less than 10, in which case you try to move laterally. Then blah, 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 0 stores X, blah, 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 blah. And then here I'm going to say else. It's going to try to move down. Good. Okay, so this won't have weird bugs then. So either you're going to move left and right, or you're going to move down, or it's going to try to move down. So no matter what, and then it's good because then it doesn't try to save the piece if you're just moving left and right. So for A is 1 to 4, and they won't interfere with each other because they're on separate loops. So this is perfect. There won't be bugs that way. You won't be able to place a piece diagonally. Okay, so for A is 1 to 4. That's the check. Right? And then if the check tells you what T is, and T is all the information that you need to know for this. So that'll just tell us what T is, which is perfect. That's what it should be. T should be set to 1 at the start of this, though, I think. Right? Right? Because yeah. Oh, wait. But T should be set to 1 there because this loop is checking for it. So for the first iteration, we need to check. So, yeah. There we go. Okay, so good. We need to set T to 1 each B loop, which we're doing. And then this is another thing we have to do. We actually have to save. This is what I think we should do if it helps it go faster. So see how I'm saving L5 and L6 or L4 here. That's not good enough. I'm going to have to save it for each loop, but I want to save it if only if I'm trying to move. You know what I mean? Like if I'm trying to move, because well, okay, let's see. Let's see here. So here's where I update L4 and L5, right? Okay, so I update them, and then I check. What's this? Right, that's the branch. If I check, so now I want to check which one. If A is 1 to 4, if it checks it, I want to see which one of those. I only want to save it if I need to, because this will save on time, I guess, because we have to hack it so much to make it so, like, quick. But, essentially, like, instead of just doing 0 stores t, I actually have to restore the old position, basically. If you know what I mean. Like, I actually have to take L5 and L6 oh, and by the way, down here at the bottom, I'm not going to use L6 and L3 anymore. I'm actually going to use our coordinates to store the new ones, because that's what I'm fixing right now, is I'm making it so that it'll always be, our coordinates will always be correct after this point. So it'll save the old ones, basically, or it'll use the old, it will store the old ones back if t is 0, if we're storing 0 as t, which means that we did not make a valid move at all. Okay, so, but we need to save them each iteration, probably. So we could, what I'm saying is we could save them here. Which is feasible. I mean, it's fine. We could save them here. That's not a big deal. Or, even better, well, okay. We'll see how slow it is. I was going to try to put it in the branch, but I guess I'd have to put it twice. Okay, I don't know why it's redrawing like 5 times, but t should not... t should actually be 0 by default. Actually. Unless we're moving. So yeah, t... so yeah, t is going to be 1 here. But for each iteration, actually it's going to be 0 by default. And it's only going to be 1 if we try to move. If x, then, you know what? And this is where we're going to do it. Then 1 stores t. And this is where we're going to store the L5 to L6, L4 to L3. L5 to L6, L4 to L3. Okay, so then 1 is going to be t there. But in the other case, well, no matter what, we're going to try to move. So we're going to do 1 stores t here. And we're going to do L5 to L6 and L4 to L3 again. And now it should work. So now it shouldn't keep redrawing us tons of times. It should... oh, come on. Why is it... it shouldn't keep redrawing us. Why is it doing that? That's not necessary. Why is it doing that? It should only draw if t. Okay, so if x, then 1 stores t, and then we save the coordinates, and then we try to move we try to move the list. If the list is valid, but there was no x. Was there? Right, g was not, so x should be 0. So what's t? T should be z. So why is it redrawing? Okay, I stopped it in middle. A t should not be 1. Why is t 1? That is not cool. And x is 0. Well, what's b? B is 10. B is 10? Oh, you know what? It might not be. It might have been redrawing actually, because it was trying to loop through the iteration. But why wouldn't it have moved down? Wait a minute, what's this? Okay, let's see here. Let's print something here. Let's display, let's just display bad. Which means, basically means that we're hitting a wall, or we're intersecting with a wall, basically. Hold on a second. Sorry, I have a call. Yay, McDonald's wants to know how to make their stores better or something. And needed my advice on. Anyway, okay. So, oh, that's brighter. Anyway, that means that I can't upload these as separate episodes, and I have to kind of put them all into one chunk or something, which might be easier for you guys. Let's just run it and see if we hit that bad. Okay. Bad! Very bad. Why is it doing bad? Right. That's why it's bad. Because it's not, because derpity derp. You know those derp moments? So I actually have to change this to an if-then statement. So I only want to do this thing right here, this changing back, if there's a fail, if t is 0. In which case, yes, I guess I could do it like 3 times, which would take forever, but whatever. Let's just... Okay, please don't redraw. Yes! Thank you. Okay, this is so cool. I can move like left and right without it going down. It is going down, but it's just going to be a lot slower, basically because like it's spending so much time redrawing that it's like, okay, we redrew, and that only took 1 iteration. So yeah, now we have a lot of control. Now it's going to keep going down. Boom, it hits. And bam, next piece. Nice. Nice, nice, nice. So I don't know what to do next. There's multiple things we can do next. Now I shouldn't be able to move left. See, I can't move left. So that's good. So we got the walls in there. We got the floor in there. We can stack pieces on top of each other. I should be able to put this piece like right here, for example. I should be able to press down. I'm gonna add that now so that our testing can go quicker. So let's do that. Let's say if G, if G equals 20. Wait, what? If G, and what I'm going to do is I'm going to store 9 into B, not 10, but 9, because then on the next iteration, we'll be able to use it. Because basically what happens is we're already in a branch that says we're not at B equals 10. So I don't want to change B to be 10 and then be like, oh, why isn't it working? So we're going to change B to 9. So basically it basically just speeds it up a little, just enough to make it observable effect, I guess. It won't be instant, but it's okay. I think this is going to be button 34, so let's try that. If I press down, it should be faster. So down, yes, it's doing it basically faster, which is nice. Cool, and then I can press down, and that lets me test it. Now this is slow, but in the future maybe we can recycle the logic and use something like characters, who knows. So press down, good, that stacks. Cool. I like it. That's cool. Cool, cool, cool. Okay. So our Tetris game is working so far. What else should we do? Should we add more pieces? I kind of want to add more pieces. So we pick a random color. Now we should pick a random piece. How many pieces are there? There's lots of different pieces. And I think the L pieces go both ways. Okay, so once we pick our random color, then let's just reset R to something again because we don't need it. I think there's 7 pieces. So if R equals 1, then we'll do this. Right? And so this will just be really long. So like if R equals 2, then we do then. If R equals 3, we can get rid of the thens and ends if we just do 2 if R equals 1s. But I don't know. I think each piece always has 4 pieces too, right? So yeah. Yeah, for the next one, let's do 12s all the way across for the L5. And do the flat piece, because the flat piece is cool. Let's do 5, 6, 7, 8, 4, 5, 6, 7, I guess. Whatever. I don't even know if it matters too much. Remember, I'm not claiming to make the best Tetris in the world. Or anything that remotely close to it. In fact, this is probably an under average Tetris game, especially since it's written in TI Basic. So usually if you want a good Tetris game on a calculator, you'd write it in assembly. Okay, so there we go. R equals 3. Let's do it going the other way. So we'll do 4, 5, 6, 6. But we'll do 11, 11, 11, 12, I think. Right? Doesn't that flip it, kind of? Vertically or whatever. We flipped it one direction, so that's something you can't do by rotating. So yeah, if then, at least if it's not symmetric. So that should work either way. It shouldn't matter how we flip it vertically or horizontally, as long as it's just one and not both. Okay, so here we go. We got the flat one. Let's do 5, 5, 6, 6. And let's do the little square piece. So 11, 11, 12, 12, or 11, 12, 11, 12, I think. There we go. They gotta be different. Okay, there we go. And then if R, oops, not Q. If R equals 5, I think, is where we're at. Yeah, because that's 4, 5, 6, 7. Okay, so there's 2 more pieces I'm thinking of. Are there 8 pieces? Because there's 2 types of else. Oh! No, there's only 1 type of this, the plus thing. Kind of. But it's not a full plus. So, 6, 7. So let's do 5, 6, 6, 7. Right? Or 4, 5, 5, 6, I guess. Stores L4. And then 11, 11, 12, 11. Stores L5. Okay, that should give us like the plus type piece. And then there's 2 more pieces which are mirrored to each other across the origin. Or across, sorry, they're flipped. Oop. Okay, so these pieces are going to be, it's like it's also 4, 5, 5, 6, right? But here it's going to be 11, 11, 12, 12. Right? And then here is going to be like basically the mirror image of it. 7. So we're going to do, it's going to still be 4, 5, 5, 6. Which there's a lot of those. And then for this part, we're going to do basically the opposite. It's going to be 12, 12, 11, 11. And those are the 2 like S pieces, basically, whatever those are called. So there we go. We have a square piece. The square piece works. And we should just get random pieces now. And that's really cool because now we have something that kind of looks Tetris-y. Which is pretty cool, actually. But it's really, really slow because we're drawing lines. And that's why it's slow. And it's even slow. This is probably slower than the Tetris that I made before on the TA84 Silver. This is so cool though. I really like the fact that it's colors. I think that's like really cool. Now, when it comes to flipping, that's going to be really confusing if I want to do it the way that I want. Because essentially, I want to do it across the center of a piece. Not of a square, but I want of the entire piece. I want to flip it across what the actual center of that is. So in this case, it wouldn't be flipping at all, right? But in the case of the 3x2 one, it would be flipping around kind of that center line, which is technically impossible because it's an odd number and yeah. But yeah, I don't want to flip. I don't know. I don't know. I know the way I did it before was I essentially flipped. Wow, did it just erase the tops of those pieces? That was so mean. I'm actually playing Tetris right now when I should be programming. But yeah, this is kind of cool. Yeah. We need to be able to flip pieces, is basically what I'm getting down to. Flip pieces is the next thing on our to-do list. So there's our pieces. We got them all in there. They seem to work. If there's any issues, we'll probably notice it. Okay. Oh, let's see here. Yeah, we don't have Tetris until we can flip pieces, or rotate. Flip? Rotate. Not flip. Rotate. It would be cool if we could flip pieces, but that's not how Tetris works, I guess. I guess I should use the second and mode key to do that. So we could do that here. And then basically what we do is we treat it exactly how we'd treat a lateral movement. So x would not change, x would stay 0, but we would store it in another variable, which we should set to 0 definitely beforehand. So we can call that, I don't know, y? Are we using y? But y doesn't sound correct. It's like, it's not correct. In R, we could use R, but R is being used by choosing our random piece. But once we choose our random piece, it's like it doesn't really matter anymore, so R could kind of stand for rotate. But then we don't know what piece we're on, and it would be cool to be able to check. Rotate. Maybe Q? Are we using Q? We'll use Q for rotate, because it's a weird, or theta. We could use theta. Do we use theta already? We do. I thought we do use theta somewhere. Don't we? I thought we used theta. Yeah, if theta is not pi. Dang it, we can't even use theta. I already used theta. Okay, sorry. I should, we should not use theta. Okay, we should use... I should store it into, like, list theta, actually. That other thing that saves the background or whatever. I should actually store that into, like, list theta so that we can keep track of whether the background exists. I'm just going to store it into W. We'll just store it into W. It'll be W. So, if G equals, and we'll do 21, 22, 1 stores W. If G equals, we'll make this 21, and we'll make -1 stores W. And that way, counterclockwise is positive. So, which makes sense, I guess, in most math standards. But now we need to flip it, which I didn't want to do, but I guess we should. And what's nice is we know R, so if we do want to cheat and just say like, oh, you can't flip this square piece, which is dumb, we could do that, which we don't really need to, but I don't know. I don't really even... Given 4 pieces, what's the fastest way to flip them? Somebody help me out here. I don't know what to do. I'm not so pro at linear algebra type stuff but I'm sure there's like some pretty smart ways to like do that. Oh, and this says if x, so I'm gonna say if x or y or w. Yeah, then one stores t. Wait a minute. Wait a minute. This end should not be here. It should be here. Right? And then if w, am I mixing I'm mixing these algorithms together. If w, then I'm going to add I don't even know what I'm doing. I think I'm going to get their average or something and then truncate it, I guess. Maybe. Yeah, because that'll kind of treat them this... That way it'll be kind of deterministic how it works. Like, you know what to expect. Even though it's not necessarily symmetric, like, you'll know... No, because I should truncate it after adding 0.5, actually. So it kind of rounds up. Yeah, so if w... So I need an average x and an average y. So my average x is going to be s, my average t is going to be, or average y is going to be t. So this is crazy, but I think it'll work out in the end. It's kind of mathy, but, or it's really not that mathy, but it's kind of messy. But basically what I'm doing is s and t are going to be my average values for x, and so I'm trying to find the center of the piece, basically. So if w, which means if we're trying to rotate, then I'm going to add to s what the x value is. So I'm going to do L4A plus s stores s, right? And then I'm going to do a then, because I'm also going to do that with the y, of course. Why not? Plus t store is t, right? And so now I have their sum. And to get their average, well, first of all, I want to be out of this loop. Right there. Well, actually, first of all, what I should have done... Okay, this is what we're gonna do. I'm gonna separate us from that loop by putting an end there and then deleting an end here. Okay. Then I'm gonna put a thing here that says if x, then do this. Else, because we know that it's either x or w, else if w, then blah, do that. End. And what's this end? This end goes to this. Right. Okay, so else do this. If x, else do this. We don't need the if w, then thing. We don't need it. So we need to do a for loop and end that. For A is 1 to 4. Yep. So we know it's W. We zero stores S, zero stores T. Don't need to be in here. Okay. So now we kind of have their averages. So if we divide by 4, S divided by 4 is going to be the average. Okay? But now we want to round it. So how do you round some, like, let's say it's 0.6. Well, I don't want it to be 0 because if we just do integer of that, then it's if we just do integer of that, then what do we get? We get 0. So how do we round it? Well, what we can do is we can multiply by 2, in which case 0.6 times 2 is going to be 1.2. 0.4 times 2 on the other case is 0.8. So if we integer either of those, we'll get 0 and 1 as our results. Which obviously, which then we can add. No, wait, hold on, I'm trying to think. And then do we divide that by 2 again? Because if we divide that by 2 again, we'll definitely not get 1. How do you round up? Do you just add 0.5 and then take the end? Yeah, that's what I thought. What was I thinking by multiplying by 2? Yeah, I'm pretty sure you just add 0.5, right? And you just take the int of that. You know what I mean? And that way, if it's like 0.4, well, even if you add 0.5 to it, it's 0.9, it rounds down. But if 0.4 plus if you have 0.6 and you add 0.5, then it's like 1 point blah, and then, yeah. So yeah, this will give us our closest, our center pretty much, which is really nice at helping us, because it gives us like a discrete center too. It doesn't even give us like a wall or something. Like, it actually gives us what we can do is we can just go with the piece that's assigned. Oh, you know what? We should do int though, because if we add 0.5, it might be easier to flip around. We don't want to flip around the piece. We want to flip around that. Do we? Because that's the thing. Because if it's an L piece, we kind of do want to flip around a piece, in a way. But it's not a big deal, I guess. Okay, anyway, those are kind of our centers. I guess what we need to do is we need to do a loop and flip everything across those centers or something like that, I guess, as if that's the origin. And now I am like going to completely confuse myself because I'm not used to doing this particular operation right here. It involves reflections and things that I haven't been working on when it comes to math. Okay, so we go through each piece. We check L4A, L5A, L4A. L5a plus t. Okay. So we... Wait a minute. Okay. So if we want to flip something if we want to flip an integer about another integer, we should get an integer. So that should be a closed operation either way. So that should be okay. How do we actually flip it? We want to flip it across both, right? Because if we flip... Wait, no. Will that work? Does that count as a 90-degree rotation? What's a 90... So like everything in the upper left should be in the upper right. But everything in the upper right should be in like the bottom right. So it's like, it seems like everything to the left should be flipped to the right. Everything in the top left quadrant should be... How does this work? Because we're not flipping, we're not rotating, we're not flipping everything irrespective of where it's at in the other dimension. Like, it actually matters where it is. But we're doing it in like a square, not necessarily a circle. Right? Right. So that's where like negatives kind of come in. Because we can treat them like negatives, I guess. So maybe I should get like a piece of paper for this and kind of work it out on paper. Because this is confusing. Okay, we're going to do this. We are going to do this on paper. Okay, so we're going to number these. We're going to say like this is 0. 1, 2, 3, 4, whatever. So like for each block here, it'll actually have like a value associated with it. So like this block will have the value, for example, it'll be like 2, 1. Like for x, y. Because that's like its corner, right? So basically what we're going to do is we're going to try to flip these blocks around some point that exists, right? So we have some point like here, like this is the point like 2, 2. So we're going to flip, or we're going to rotate on 2, 2. I guess. So if we're rotating like clockwise, for example, or let's just go counterclockwise because that's when W is 1 or whatever. So that means that piece will move there. So if we're given 2, 1 and 2, 2 as our rotate point, how do we get this point, which would be... this point would be 1, 1, I guess. So how do I get these two and then get 1, 1. So basically, if our rotate is 2, 2, then we have a column of starting points, right? And which would be 1, 1, and then here, this point is 1, 2, and then this point is 2, 2. Okay, so I want this one to go down, I want this one to go right, and this one to go up, based on 2, 2. These points should change to the one kind of left of them, I guess. And if we just generalize it, it should work for all the pieces. So, So if I I can start off by subtracting it, because that's kind of the most intuitive thing to do, to treat this kind of as the origin. But before I do that, I want to find these end where these are supposed to result in. So that I can just subtract from there. So 2, 1 obviously is supposed to go to 1, 1, and then 1, 1 I think is supposed to go to 1, 2, and then 1, 2 is supposed to go to 2, 2, and then 2, 2 is supposed to go to 2, 1. So if I subtract 2, 2 from each of these, what do I get? I get 0, negative 1, goes to negative 1, negative 1. Then I get negative 1, negative 1. Well, I could just do an arrow like this. Negative 1 is supposed to go to negative 1, 0. Negative 1, 0 is supposed to go to 0, 0. And then 0, 0 is supposed to go to 0, negative 1. If that makes any sense at all. Whew, this is crazy. And you know what? I want to test this on like a piece way out here in the positives. So like 4, 4, right? This piece should move all the way up here actually. Right? So 4, 4 should actually become 3, 0. I think. Which means that 2, 2, when you subtract it from it, that becomes 1, negative 2. Does that make sense? This is weird because I'm not flipping. I'm trying to think how this works. So I need this to be preserved and then all of these to be preserved. All of those properties. And once I do that, then I just have to do it both ways and we're done. We did it. So we found the average point. Yeah. We found the average point. We add. Okay, I'm gonna zoom out a little bit. I'm not sure how I would do this. But basically, it looks like whatever the right number is. In these cases, it becomes like the left number. See, like the right number is -1, the left number is -1. The right number is 0, the left number is 0. The right number is 0, the left number is 0. But here, the right number is 2, the left number is 1. And is that even right? I need to double check that. No, this would be 3. Wait. I lied. How does this work? Right! This makes sense. Okay, so sorry, I did this wrong. This is 3, 3. Right? And it goes from 3, 3 to 3, 0, which means the right number actually does become the left number, I think, in each case. So that what we know for a fact is this number basically just gets moved there. That's basically what's happening. And my camera's being stupid. This number definitely gets moved here, I would say, in every single case. But what's the new right number? I mean, the new right number depends, right? Because the magnitude of the x becomes the y. Right? Or wait, what does this mean? This means that whatever the y value was, that's the new x value. So if the y was 2, the new x is 2. If the y was -2, if the y was negative, it was down here, like negative, or I guess in this case positive, then the x is positive. Is more positive. Oh, you negate it, don't you? You negate the opposite one. Right. So what's this? So this would become 1, 1, not 2, 2. Right? And then you'd subtract 2 from each of these. In which case I did this wrong too, because this wouldn't be up here. This oh. Wait a minute. Right, I'm not flipping the piece, I'm flipping the dots. This is frustrating. If I'm flipping the upper left dots, then that kind of changes things. I might not want the center piece to be the piece, but we can change that later. This would be here, which means it would be 3, 1. Which means that this would be -1, which means that the right one is the negation of the left one. So, yeah. Okay, so overall, I think I have an idea of what's going on. I'm not, like, very precise in my understanding of, like, how it's going to work with these integers very well. But essentially, what we need to do is, it just depends on whether w is positive or not. Whether we are negating, we're basically going to flip the x and y of each one. And then and it'll be cool. So yeah, it'll be cool. We can save it. We can save a extra variable into like v or something. So we're gonna save L4 of A. We're gonna save it into like v, and then we're gonna save. Well, let's just look. We're gonna pretend we're gonna swap them first. L5 into L4 of A, and then v into L5. Wait. We saved L4. Now we can overwrite L4 with L5. Now we can overwrite L5 with L4. Okay. So that looks like we swapped it. And now basically what we need to do is we need to multiply one of these with W and the other one with negative W. Okay, so we basically do W times that, and then we do negative W times that. And that gives us W control over which direction we're flipping. Okay, so then the final thing we need to fix is going to be this 0.5 here, because that might be basically changing what our center should be into something weirder. So yeah, let's try this. Okay, so invalid dimensions, which is fine. It's to be expected. We're way, so we're negating things and things like that. Oh no, you know what? This kind of makes sense, actually. So we might need to make the matrix taller to handle this, but by like probably 2 spaces because of the 4 long piece. But what we shouldn't have to do, but what we're doing wrong is we're not subtracting. I was wrong. I totally forgot about us shifting the things to 0 and back to the origin, basically. So we have S and T, but really we want to treat S and T as though they're the center, not as though they're where they are. So we don't want to flip based on. Wait, we weren't even using S and T here. What? We were just flipping these. Okay, so we don't want to flip. Obviously, we don't want to flip their actual coordinates. We want to flip their simulated coordinates based on S and T. So we want to subtract S and T from them and then add it back. Right? So we want to subtract S from here when we store it, and then we want to subtract S from L5, or T. Right? And then whenever we store it back, we want to add S and T. Right? And that's weird. Or I should have said minus S here, which means we bring it to the other side. So we're adding S to this side, actually, if this was like an equation. So obviously I can't add it to an expression. That's weird. But this would be like I'm adding it to that the expression of that minus T. Like that would be its value of that expression. That should be like essentially what the new value of that expression is. So yeah, so I'm adding S back to what will that work? I hope that works. Okay, we're gonna move this down a little. Now I'm gonna try to flip it. Okay, good, it flipped. Okay, I'm gonna flip it again. I'm gonna flip it again. Cool. I'm making it go up. which is a very bad thing, but it's cool that we actually can do this. And I'm making it go right now, which is a very bad thing. But cool. We can flip, which is really cool. We shouldn't be able to flip next to the wall when we shouldn't be able to, so let's try to flip, and then when we try to flip again, it shouldn't work. Which it doesn't, which is good. Yeah, so we're definitely not flipping in the correct, like, center, but we are flipping across some center, which is really cool. I want to see what another piece looks like when it flips. So the real test is to see if the square piece flips across the center. So what we can do is we can kind of, just to tweak with it, we can control what pieces we're flipping. And we can force it to be the square piece or something like that. So we can force it to be piece... What did I just erase? Dang it. Dang it, dang it, dang it, dang it, dang it. I erased, like, literally the most important... No. Do you... Like, I know what line I erased, and it's a very bad line to delete, because actually, I have no way of getting it back. Which is sad. And you know what? We'll replace it with something even better. Instead of 4 colors, let's do 6 colors. Yeah? Let's do that. Let's do 6 colors. What should we do for the last color? Should we make it magenta or green or brown or something? Should we do magenta? Yeah, let's do that. So 10, 11, 13, 14, 15, 19. How do I select? Oh! You know what? Those were in list 1, weren't they? Right. I was stupid. No, I didn't realize. I actually didn't know what line that I didn't know which line that I had erased because I totally, oops. So we added 2 more colors. Let's just, I thought I erased that line, but I didn't. It was actually, all this line was L, it was L1 of R stores C. That's what it was. That's what that line was. And we're going to change this to 6 now. So now we have more interesting colors to play with. So, yep. And the rotation isn't that bad. It really isn't. I would be okay with, like, leaving it, I guess. I mean, it really isn't that bad. You know what I want to do, though? Is I want to make it so so that you can't, like, you can't move something to the ceiling. I just want to do that because it's like it's kind of annoying to make like a buffer above the game, and it's like no, there should be a ceiling, and you shouldn't be able to have pieces off the top of the screen. That's just going too far. I think we should box it in. You're supposed to feel kind of boxed in when you play Tetris. That's kind of the point of the game, is to play in this boxed in environment where it's like, oh shoot, I wonder if I can survive, you know. It's supposed to be a tight game, you know. So yeah. We might get rid of those 0.5s. I don't know. Maybe. But let's just go up here and let's increase the size of the matrix. So the height is going to be 15 instead of 14. Okay. And then for here, we're going to change this to 15 so that we get the corners both times. And then for here, we're going to do 1 stores matrix A (15A). And what that should let us do is that should box it in so that no matter what we are, we'll never be able to rotate that long piece off the top. Actually, no, we will, which is a problem. That is a problem. I just realized. Dang. Okay. The problem with the long piece is we could technically still rotate him out the side of the matrix, and it will cause issues with there being accesses to the matrix, because even though it would be an invalid move because part of it would be intersecting with the wall, technically we still would be testing for a piece outside of that wall, and when we test for that piece, they will basically have an invalid dimensions error, which we cannot catch because for whatever reason they like to make errors stop the entire program instead of just returning a certain specific branch value or something. But anyway, that's how BASIC works. It's really bad once you learn your CS theory, but that's how it works. So what we could do is we could just expand it by 2 in each direction, and then we could expand it by 2 in each direction. And we will. Let's do it. Let's expand it by 2 in each direction. That'll make things easier. That'll make things easier. So this is going to be 2 and 16 basically, and then this, instead of being 1 and 13, this will be 2 and 14. And then for A is 1 to 15, no, this will be A is 1 to 17. So, and then we're going to add 1 to each of the matrix axes down here, where we check things. Here we go. So this is going to be a 2, and this one's going to be a 3. And then down here where we save it, this is going to be a 3, and this one's going to be a 2. So hopefully I did that correctly, otherwise it's going to be weird. So when this piece falls, oh, by the way, I want to rotate this Yeah, see how it's going up? And right. It's going up and right. So it's favoring the center is favored in the like. Okay, we're gonna stop that. Matrix A. Good. It's looking how I expect it to look, where there's like a buffer zone. That buffer outside of the wall is just so that the long piece doesn't crash the game, and it's easier to code it doing that than it is. Yep, and see that we have a ceiling too. So it's perfect. It's a ceiling wall buffer system. We have the memory for it. It's easier to code that way. Yeah. Anyway, that'll save us even the speed of our program a little bit. I'm glad I can use memory over speed here because the speed is really bad. So what else? So it's favoring too far to the right, so we can delete the X one. And then it favors up, which is smaller, which is weird, right? Which is, like, it shouldn't. But, like, you know when you rotate, like, okay, basically, it's, when I'm rotating it, it's moving it, like, up, which the Y value, oh, no. Right, the Y values on our screen go from bottom to top. So they start, or on the draw screen, are 0 at the bottom and higher at the top. So it is favoring up too much that case. So let's do that. Let's just do that. Okay, so that's favoring left. Which I guess it's kind of difficult. You know, these are okay though. For rotations, they're not bad. They really aren't. They're not perfect. Which I should be able to figure out someday, you know, because they are integer rotations, so there should actually be a best way to do it. But these are not, like, bad rotations. I mean, there's not necessarily a bad way to do it, or a perfect way to do it, given that there's, like, a way that, like, there's two competing directions or something. But, like, I don't think the 2x2 box should move when it rotates, basically. Like, that's like an easy, like, check. So, yeah. Looks like we got rotations down, which is really cool. I think I'm gonna put like hyperlink. I think I'm gonna put like links in the video or something that basically like tell when, like, that like link to when I complete a task. So like when I complete like rotations or something. What? That, no. Just no. Why did that not go down? That was bad. That was very bad. Why did that do that? That should have gone down. That was very bad that it didn't go down. Yeah, I don't know why it didn't go down, but it didn't. I hate this because I'm like basically erasing the wall. But I can crash it again. But I can crash it. No, I can't. I tried rotating. I think 2 wall buffers is enough to save us from the death. from the crash of death from the stick. Yeah, I don't know why it like floated, but that was bad. It was very bad. So there we go. We basically have Tetris. It doesn't work all the way because we need to be able to delete like a floor, I guess. Which means which basically means that we would have to like draw like the entire thing going, like we'd have to be basically like move everything down according to its color, which shouldn't do. Anyway, that's all I have for now. Thanks for watching. Alright, I'm back. I watched the movie Allegiant. It was pretty good. At least in my opinion. Just because, I don't know, I like that kind of genre, I guess. Okay, so I'm trying to remember where we were and what I was going to do. First thing I want to do actually is check where it... wait, here it is. Here we go. Okay, so I want to change this to not equal 0. The reason is because down here I'm going to change this I'm going to change this to C. So the matrix is going to keep track of what colors are in what locations. And the reason why I'm going to do that is because we're going to erase the bottom row when it's full, and then we're going to shift everything else down. So here we got this piece, and then we get another piece, and now if we quit and we look at the matrix, see we got 11s for one piece, and then, well, the other piece doesn't exist yet, but anyway, we stored the colors, so that's cool. So now things will fall and hit the ground and do whatever, but we need to move them down. So for whatever rows that there are, we need to add the code to delete them and move them down. So here we are. If T, then blah. Yeah. Sounds good. Let's see. So when do we actually do that? Well, when this happens. So if T is 0, that essentially means we can't move down anymore, and then we place the piece. So I guess the code would go here if we're going to do that. I'm guessing. So we could preserve on the speed by, instead of erasing squares, what we can do is we can erase lines. And what we need to do is we actually need to get a count of how many full rows there are. Which, this is going to be a little tedious, but in the end it'll be worth it because it'll make things run smoothly and quickly. Or as quickly as possible, I guess. So, for A. So 1, 2, no, 3, 2, I think I think it's 3. Actually, okay. So actually all we really have to do is look at the rows that are I think I don't have a lot of memory left in my camera. I'm not sure. I might have to delete some videos or something. Anyway, so to delete the rows, the only rows we need to we only need to check up to 4 rows. So for each, we only need to check the rows that our piece landed in, actually. Because obviously all the other rows are unnecessary to check because they won't have any new pieces. And we can't start checking from the bottom because then we'll be checking all of them and the bottom ones might not necessarily be filled and things like that. So yeah, I need to check all the ones here. So then I would say L5 of A plus 2, and I guess save that as Y, and that will give me which Y I'm going to be checking for a full row. Yeah. Now the thing that I'm wondering is, what am I going to do actually if actually 2 separate rows get deleted? That's an interesting thing. Okay, maybe I shouldn't do that. Maybe what I should do is I should iterate through the entire thing until no more rows need to be deleted, which sounds like it would take forever, and it probably will, but that's the only way I can think of. Because what if you have, like, let's say you have a row that has like a missing or almost Hi, I'm back. I watched Zootopia with some friends and it was a really good movie. I know that this is taking forever, but I think I'm gonna splice all these into one episode and give you guys some links so you can find things, but that's kind of a pointless thing to tell you at this time. So the last thing we were working on was checking. So I had just decided that because, oh yeah, and by the way, my my camera ran out of time while recording. So basically what I was trying to say here was, oh, what if you have 2 rows that are completed and let's say they look like this. Well, if I checked from the bottom row to the top, well, then I'd see that this row is completed, then I'd have to move everything down, but then I'd miss that this row was completed. So yeah, there's not really necessarily a good way to do that. I mean, I could do an algorithm that like stores them into a list. or that moves one row down at a time. I guess that could work too. So what I do is I check a row, and then if that row is completed, instead of iterating up, I actually stay at that row one more time and check again. But then I'll have to move everything down. I guess I should do it like that though anyway, because to move things down it would be really complicated if I try to move everything down according to I guess it would be complicated if I try to move Oh, you know what though? I'm wrong. You know what? Visually, we don't have to move everything down right away. What we can do is we can redraw the matrix. Like, we can go through, we can do the matrix little algorithm thing that just shifts everything down, and that should be decently quick. And, yeah, it will take some time, but at least it won't take necessarily that long. And then what we'll do is, after that is finished, then we just redraw all the squares, basically. Which means we will have to erase the old ones. Which means probably drawing the screen again, actually. Oh! Right. This will be fine, because what we can do is we can just redraw the entire screen. I guess we could do it that way. It'll be silly because it'll basically process all of the drops together in one go, but it kind of makes sense because it'll be pretty quick compared to what it otherwise would be, I guess. So yeah, let's, I guess, try that. So we want to do it down here. This is where we store the last piece, and right after we store it, we want to check for that. So yeah, we're going to get rid of that for loop there because it's not the right thing. And then we're just going to go through the entire matrix, and this is just going to be a matrix and screen thing that we're going to do. So, and we only want to do it if we find a row. If we find a row that had to move. So I guess what we can do is we can have like a variable, like we'll say m. So we'll say like 0 stores m. So like 0 means we did not move anything down, and then 1 will mean that we did move something down. So we're gonna do a loop, and we're going to oh, and I forgot to mention, this morning I went to a leadership kind of class thing, which was pretty cool. And there's a few people there that I knew. And it was kind of an all-day thing, but it was kind of fun. So, anyway, anywho. So, I don't know if I can use X and Y. Can I? I don't think X and Y are used really in this loop. So X here is used as kind of like a local. See, I store 0 and X. So whatever X can be abused however we want, and I'm sure Y can too. So let's go ahead and use and abuse those. We will probably have to do more codes of lines, but that is how it is. So yeah, let's go ahead and do that. Yeah, where to start? For X, is 1, 2, I'm guessing it's 11. Is it 11? I think so. And then there's another for loop here. For y is 1, 2, 13. Is that right? Yeah. But I think, but what we're gonna do is we're gonna add 2 to each one, right? And we're gonna check, because y is going down. So we want to check the y's first. Yeah, I'm trying to think. Yeah. Okay. So we want to check the y's first. And we want to go from 3 to 13 and from 3 to 15, I believe. And it should be 15 and 17 for the sizes of the actual matrices being instantiated, right? 15 and 17. Why is it so far up? Good. Yeah, it is. 15 and 17. Okay. Right, so x is 15 across, y is 17 across. We start at 3. And then we check. So we check. So 0 means that we haven't found a row. But to say that we haven't found a column for a particular row, we also need to check and say, well, 0 stores n. And what we do is we say if matrix A y x does not equal or equals 0. So we're going to set 1 to n. No. Well, fine, we'll set 0 to n. The point is, if there is 1 that's a 0, then n's going to be 1. Or let's do it the other way around. N's going to be 0, right? So usually n is going to be 0, saying that, well, there is a 0 there. But if n is 1, then outside of this loop, we're going to set m to 1. Right? So if n is 1, if n is 1, then we're going to set m as 1, even if it's just for one row. So that's what we're saying is if there's one bad row or one row that needs to be moved, then we're going to do another algorithm which involves moving everything down. Or well, I'm already doing the algorithm that I'm already going to move that in here. But we're also going to add the function afterwards. If m is true, or if m is 1, then that means we're going to have to do the graphical redraw, basically, of the matrix. So it's going to be, we're going to have a function right beneath this that redraws the entire screen based on what the new matrix is. Yep, so that's how it's going to be. So, let's see here. And I wish I had a function that could draw a square, but can't really even do subroutine. You can't even do, it's silly. DI is silly. Even someone who doesn't do, even someone who's not an expert in programming languages, they should realize how silly TI is. And I'm sorry for complaining so much about it, because this is a series, and well, I loved it, but now that I know so much more about computers and things, it's I can see why there's not many people who program these, I guess. Yeah. So, here is where we're going to do another, I guess, loop. Or no, wait. Okay, that's wrong. Okay, so that's the check. This is where we're going to do something else. Okay, so not only is it going to set 1 to m, but we're also going to subtract 1 from y. Right? Because we want to check this row again, basically. That's why. Well, we're going to do that after we do something with the row. So once we find out that they're all ones, we're going to write whatever's above. We have to shift everything down then, starting from the row that we're at. So basically, like for example, if we're like checking this row, let's say this is like a row and these are all ones. Well, as soon as we find that out, we actually have to move everything else down. Not just the next row, but everything. Which is crazy. I know, but it really is so. I mean, just kidding. That was from a song. Just crazy, I know, but it really is so. I'm my own grandpa. Okay. This is ridiculous. I shouldn't go all the way to 13 because the problem with that is it's going to copy ones down. But I'll go to 12. So that should work, I guess. So I'm gonna, instead of using y, I'm gonna use another variable. I guess I'll use p. For p is y to 12. And I don't even know if I should do 13 checks. Maybe I should just go to 12. Because I don't want to copy the top row like above it, like the walls above the top row. The top row shouldn't get filled anyway. That's kind of, I mean, theoretically, I guess it could get filled. Okay, we won't think about that right now. Let's just worry about the game, and it won't be a perfect game, I guess, but I guess theoretically, if the top row was filled, we would just replace it with, I guess we could check for ones anyway. Where we copy things down. Okay, I guess what we can do is we can copy things down. We can leave it at 13, and then we can copy things down unless they're ones, in which case we copy zeros. Because 1 is not going to be a piece color. 1 is going to be a wall. So as long as we don't copy walls down on that last iteration, I guess that's okay. It's just going to make it a lot slower though, unless maybe we can do a check for if p is 13. That might be okay. Because row 14 is going to be ones for sure. But anyway, we're going to do x's from 3 to 2, or x? Something's fishy. No, y should be the one that goes... What? No, y is taller. What am I thinking? Yeah. Y is the one that goes to 17. Yeah, so we do y to 15, and then the 16th row is ones. Right. Right. So we can do y to 15, and x goes from 3 to 13 here, and we're going to store store the next row. So matrix A, well, first of all we're going to check if P is 15, I guess, because, well, no, we're going to go to 14, and then what we'll do is we'll just add another thing here that's different. So we can say for P is P to 15. Does that work? PP? Does PP work? I think it should work. I think this first variable, although yeah, because it just assigns it to itself, I guess. Or let me just do that. Or wait, no, we're just doing one row, so what we need to do is we just need to do a for x. For x is 3 to 13, and then instead of putting p in here, we just put 15. Right? Because yeah. And then here so here we just store ones, or I mean zeros, sorry, into y comma x. Yeah, there we go. And here we store, yeah, so okay, I guess we did do it the perfect system theoretically, or whatever. So we can fill up to the top of the box, and we just handle it by and we don't put a y, we shouldn't put a y here, we should put a p here. I don't know why I'm putting a y here. P here, and then here we don't put either, we put a 15. Yep. Okay, so that should be the correct thing. And then we subtract 1 from y. So basically what it does is anytime we have a full row, we're going to shift all the rows down and like basically consume that row in the matrix. And then we will have a brand new matrix, and we will have stored 1 into M. So we marked that, hey, check it out, we need to redraw our like background thing, or we're going to have the background saved, but we basically are going to need to redraw the matrix. So I'm going to have to, I guess, do some lines for that or something. I don't know. So how do I make sure I'm done with this? If t0, then, so we're up 1 and 2, 1, 2, 3, 2, 3, 4, 5, 4, 3, 4, 3, 2, 1, 0. So after this end right here, yeah, because there should only be 2 loops outside of that anyway. We do another if. So we say if M, then end. So the first thing we're going to do here is we're going to recall. Well, I guess we're going to clear draw, and then we're going to recall pick. Pick 1. And then basically we're going to do the whole thing again with the for y and z's. So for y is 3 to 15, I think. Right? Because otherwise it would be 1 to 13, right? And then we're going to do for x is 3 to 13. Because x is 11. Okay, and then we're going to draw. So we're going to get matrix A of yx and store that into C. And then if C does not equal 0, or does not, oh no, 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 no. 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 Then end. And there is a very big issue that I just realized, and this is a very, very bad issue. See these 12s? Yeah, they will cause a problem unless they're unless they're zeros. If those are 12s and they're meant to be black, then those will cause issues because they will actually count as blocks, which is a very bad thing. I don't want 12s stored in the matrix because 12s will make it look as though there's a color there. I could say if C equals 0 and and C doesn't equal 12, just in case, because I mean it's not going to hurt it if I just put this here, I guess, because it's going to treat black the same as a 0. So yeah, I could also do that here. I could put an or. So if it equals it, I should put an or, because that basically says like, oh, if it's black. So if it's 0 or 12, that means it's black. And down here it says if it's not black. So it's both not 0 and not 12. So that's why I need an and here, because it's a not equals. Logic, 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 logic. So yeah, now we have like 6 ends here. 1, 2, 3, 4, 5, 6. Yep, that sounds about right. Okay, so now that we have all those things, we got our coordinates, we have C, we have our matrix, yeah. So now we need to draw according to where we are, which is going to be 4 lines, but we're going to draw a color by C, but we also need to subtract off whatever we need to add O, of course, but we need to subtract off whatever the coordinate difference is. So we might have to subtract like 3 from X and 2 from Y, or I guess, or 3 from Y and 2 from X. So that, yeah. So yeah. Where's line? So 3 from Y, 2 from X. Or instead I could do 1 to 13 and 1 to 11. And then I could just add what I'm supposed to add here and make things easier on myself down there. Okay, so yx and then y plus o, x, and then c, and then y plus o, x plus x, and then y plus o, x plus o, c, then y plus o, x plus o, y, x plus o, and then y, x plus o, yx, and I forgot a c up here. Okay, so theoretically that should work then, I think, hopefully. So the only way to find out, I guess, so it looks like everything's working so far. The only way, really the only way to find out, the easiest way here is to actually, well, I guess complete a row. So we have to actually play Tetris here. And yeah, let's play Tetris. Woohoo. Okay, this is fun, by the way. Playing like the slowest Tetris in the world. It's so slow. I hope T.I. watches this and has the attitude of like, oh, oops, we should have made it easier to like draw squares and stuff. Or something. Or at least respond. Oh, come on, please work. So is m, what's the value of m? M is 0. It's okay. It's okay. I don't get... What? Why am I not... Oh, is it because... No. I had a row. See? Oh my goodness. Let's go down. Yeah, something's weird. So we have a row in here still. And the row never got deleted. And we also didn't get m marked as 1, which it should be a 1. Well, at least our for loops aren't all screwed up and ends being reached where they shouldn't be, I guess. But logically, our program is not functioning the right way. I don't know why. So let's think about what happened here. So so what we do is we check. Once we turn m to 1, then it's permanently 1. We can't set m to 0. N, on the other hand, once we set it to 0, we can't turn it back to 1, but we check it for different rows. If it's ever passed through here as a 1, then m should be set. So that means we never reached this code. If AYX equals 8, or AYX equals 12, 0 stores n. And we check from x's 3 to 15 for y 3 of 13. 3 to 13. So what's matrix A of 3, 3? Well, it's definitely not 0 or 12. Oops. Yeah, so none of those. 3, see, 3, starting at 3. It's 15, 15, 13. All the way. None of them are 0s and 12s, all the way to here. So what's the issue? Why didn't it do something about it? I might add print statements to this just to make sure things are working, or things are being reached when they should be reached, because if we don't know where it's going wrong, it's going to be harder to actually debug this thing. Okay. If m, well, There's 3 n's before this if m, right? So display 1, display 2, display 3, then we're going to display 4, and here we're going to display 5, here we're going to display 6, and then I guess we'll display 7, and then we'll display 8, 9, 10, 11, 12. Ooh, this is going to be a very messy Tetris game. I gotta display 3 and 11 too often, so maybe I should get rid of those. I'm glad that it's reaching that 11 though. That's a good sign. Wow, it's gotta hit a lot of those, doesn't it? It's very interesting running a debug on a calculator because it basically it has to switch to what we would call the debug screen. So this is a very it's almost kind of funny. Yeah, I don't know. I don't think I've done something particularly like this before, but it's kind of funny to watch. Oh, this is nice. Oh, I hope it fits. That is, okay, so if we do this again, we're going to get rid of 3 and 11 because they're the most annoying. And we might get rid of 1. Okay. Okay. You know, I should just start the matrix with a row at the bottom, actually. We don't have to do this, I guess. 11, 1, 1, 1, 1. And why did it hit? No. No, I want to see the output. Oh, it doesn't let me see the output. That is not cool, TI. That is not cool. You encapsulated my execution of that program in such a way that I can't even go and see the history of the output of it. Are you for real? Why Texas Instruments? Why? 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 I'm gonna start a new company. I'm gonna call it Illinois Instruments. And we're gonna make our own calculators. And it's gonna be better than Texas Instruments because we're gonna have a functional language in our calculator, and we're gonna be able to debug things if we need to, but we shouldn't even have to because it's gonna have a strong static type system. Yep. Forget Texas Instruments. Just forget them. We're better. Buy our calculator. Don't buy Texas Instruments calculator. Our calculator's better. 1, 2, 1, 2, 3, 2, 3, 4, 5, 4, 3, 4, 3, 2, 1, 0. Actually, there's something I should technically change, which is I should actually put the if m inside of the t equals 0 thing. But that still doesn't explain, or sorry, the t equals 0 is that the t does not equal 0. If t equals 0, so if we aren't moved, that's the only time where we actually check, and it's the only time where m is going to be 1 anyway, because otherwise we're going to be stuck in an infinite loop the next time we try to move, because m will just be 1 still, because we only set it when we check anyway. So, but still, why isn't m gonna be 1? If n for y is 3 to 13, 1 stores n. For x is 3 to 15. If yx equals 0 or yx equals 12, 0 stores n, end. Why? There. We're checking the right ones. None of them are 0, so n should be 1. Right? It should be. It should be 1. Okay, this is what I'm going to do. I'm going to keep the same matrix before so we don't have to play it again. I guess the only thing we'll have to do is put down a piece. So here we draw the background, right? And then we set the matrix up here. Right? So I'm going to do if 0, then, and then here where we fill the matrix, I'm going to skip that. So it's just going to, we have the same matrix as before. So I'm going to fall here. Bam. Zeros all the way. Do you see that? Do you see that? That is where our error is. Zeros all the way. So we have it shouldn't be 0. Because we have a 13. We have no 12s, we have no 0s. right? Am I checking the wrong... Am I checking the wrong... Like, the wrong width or something? Like, it's 11 wide, right? So it should go from 3 to 13. Right? That's what it should be. Oh! Heh. 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 Okay. 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 I'm sorry. That was totally my fault. I can't believe this. Okay, so there's invisible blocks down there. I'm gonna move this down. It's gonna hit them. And bam, we got a 1 and then zeros. And it worked. Okay. I think it worked. And the reason why it looked weird, which I know I don't sound surprised about it looking strange or whatever, but I think all that was I switched the X and the Y's. But other than that, I think it actually did work decently okay. Although I'm not sure what the blue was on the right. That was kind of weird. So let me switch these to the correct thing. But those blue ones were kind of weird. I don't know what that... I'm kind of confused what the blue was. Yeah. What was the blue? There shouldn't have been a row of blue. I don't think. I don't think there should have been. Let's hold on. Let me erase this if 0. So I'm gonna change this to just if 1. It's a debug if. Uncomment. Okay. So, oh, I forgot to turn off the printing of the 1s. Dang it. I forgot to turn off the printing of the 1s and 0s. It shall print 1s and 0s between each piece. My bad. But we're resetting it so that we can actually observe it falling. So there's 2 pieces up here. And yeah. Guess this is, yeah. What do you guys think of like the icon in the upper right? Like it's like this cool little like circular thing. It's, you know what I mean? It's like that little spinning whatever. Like what is that? Like I know what it means. I know it means like it's computing. But like why did they go with that? Like you know the old TI calculators, like, you know on the other one, like, it's just like a little dot, like 2 pixels at the very upper right, like 3 pixels that move left and right. But now it's like a little circle, like, it's like, I'm computing right now. Okay, watch the prettiness. Watch the prettiness. Okay, it fixed the matrix. No. No. Why did it do that? Why did it... Wait. Stop. Before it draws to the matrix, let me check the correctness. That looks good. I think. Yes. No, the matrix is perfect. It looks good. Yeah. So, okay. So our algorithm works. We're drawing it wrong somehow. But the data in the matrix looked like flawless to me. That looked perfect. It looked like it took out exactly one row, exactly how it was supposed to. So that worked perfectly. I don't know why we're drawing it wrong somehow. I think. So yeah. I think X should go from 0 to 10. And Y should go from 0 to 12. Right? Maybe? Well, when we oh, wait. Well, when we save our things into lists, are we saving... What exactly are we saving? Like, I don't even know what the... See, like, we have, like, these coordinates that I, like, started off with, but, like... But, like, what even are they? See? Like, see, I plot from Y 0 to 12. Right. Right. Oh, Y is 0 to 12. X should go from 1 to 11. So Y should be from 0 to 12. X should be from 1 to 11. Like that. That's how it should be, with the X's and the Y's. That's the correct X's and Y's. And that's why I add 2 to the X because of the buffer and add 3 to the Y because we're starting it literally at the bottom at a zero-based plotting and the buffer. So that's 3. And that's why we do 3. So what? Wait, okay. We're gonna speed it up again by debugging out that statement so that we can try to delete the... Oh no. You know what? Dang it. No, we can't do that. Not you. I know you guys are probably wondering, like, where did that collapse come from? So long story short, in the past I've tried to actually prove the Collatz conjecture. It wasn't with that program right there, but I just felt like looking at the numbers again for some reason. But yeah, actually, it was kind of just a fun exercise, I guess, that I wanted to just... Why am I scrolling down? There's a if 0. Here we go, if 1. Okay. So, long story short, I wanted to prove the Collatz conjecture, and I actually got, oh no, you know what, go to that, go to where I'm printing. No, it went back to the top of the while one. Oops. Okay, where's the prints? Are there any prints? Prints. Display, here we go. Display and delete. I don't want you. So I try to actually prove the collapse. I came up with I generated, what did I do? I basically came up with a system of, I came up with another tree, not the collapse tree, but a proof tree, or a schema proof tree that basically came up with proofs of schemas, like algebraic schemas of expressions of numbers that were proven to be solved under the collapse conjecture. And that proof tree was also, it actually did have like a self-referencing part to it. But the thing is, like, I only was able to prove, well, actually, no, before it had the self-referencing part, I had actually at one point thought that I had solved it. Okay, there we go. It kind of worked. It kind of worked. It kind of worked. It kind of worked. Why is it drawing weird? Though, that's... It shouldn't be drawing weird. But yeah, looks like our Tetris actually, like, works, though. Which is really cool. That's cool. It has to redraw the whole screen when we do that because it's easier that way. We technically don't have to do that, but it's just, I guess it's faster and it doesn't take a long time to do it anyway. It looks choppy, but it is fast. So we'll just stick with it for now. It's kind of cheesy, but yeah. I think I found our issue. I don't know why, but I put a 0 here instead of an O here. So yeah. I guess that was it. I knew there would just be something silly like that. I knew I had just done something wrong with the coordinates. Okay, so I'm going to turn off this lamp so it's easier to see. So here we go. I'm going to zoom in. And what I'm going to do is at the bottom of our, or sorry, at the end of the video, I'm going to have a link to the end where I just play it. And I'm going to let people just see the link, and they'll just get to see me kind of play it. So that way they can skip all the coding if they want. I actually don't want you guys to necessarily skip all the coding every time. I want the coding to be like legible or discoverable, I guess. So I want to kind of make it linked so that if there's anything that you just kind of want to see, but you don't want to see the whole thing, you'll be able to find it through links. Kind of the idea. So here we go. We're playing Tetris. Playing Tetris, and it's fun. Woohoo! Tetris! And I guess I could speed up a section. I should make it so that I like lose if I pile all the way up to the top, but what I should do is just be like, well, I guess you can't lose because it's so easy that you're basically guaranteed to win anyway, or you're guaranteed to quit after a while, which is kind of sad, but yeah. We pretty much made a type of Tetris game. I guess I should put an ending that says you lose after one iteration, maybe. So if you Oh, there we go. We cleared out that bottom row, which is cool. Yeah, so I made Tetris like I promised. I guess. If you consider this Tetris. We could make a losing screen. I guess we should. It's not a big deal. This is fun because I'm actually recording and I'm playing on my calculator and I'm watching like the recording as I play, so I'm like playing on my camera, but like controlling my calculator. So, yeah, it's pretty fun. Woohoo! I should make, yeah, I should copy this footage and then speed it up or something. And maybe put it at the beginning, I guess. Even just for people to see kind of what the end result looks like. But yeah, there we go. So let's zoom out a little, and I guess what we can do is we can go for that. I'll turn on my lamp so I can see what I'm doing. So to make us lose, we can basically we can have like a test variable that like if we're not able to move at all, or hold on, how do we do this? So we need to set a variable, let's set it like k or something. So if we move successfully, we need to set k into like 1 or k to 0 is the idea. And then if k is 1, that means we've shown that we have not been able to move successfully at all. Right? Does that sound right? Or maybe when we introduce a new piece. Maybe that's how we should do it. Like if we introduce a new piece and it's on top of other pieces, then that's like a no-go. That's like, no, I can't put a piece. Like it doesn't matter if pieces move down. Like if we place a piece and it can't move, if it doesn't move down but it gets placed where it's at, that's fine. But it's when we try to introduce a new piece and it's like, well, we can't place a piece there. That's like an issue. That's like, no, you can't do that. That's bad. Like we shouldn't allow that particular thing to happen. You catch my drift? So we can do that, I guess, here. So we can do like 0 stores k. And then down here, we can do a loop. So we do for end. And then we say if k, then, and we do a stop here. We do a display, game over. Game over. If k, then display game over and stop. So we do this. We say for a is 1 to 4. And I guess we just check the matrix. And we say if something, then one stores k. So if our matrix, and I think it's alpha, wait, okay, alpha, L5, and then L4. And I don't want an or, I want to say and. If it's both not 0 and not 12, then we know that there's a piece there. Right? And then we want to store one is k. Now, I need to set their parameters, but what are their parameters? Okay, so we add 3 and add 2. That's how it works. Add 3 and add 2. Yep. Ow, my foot. Okay, we should have stored that into K or something. So, or into another letter, like B or something. But anyway, if L5, which is the Y, and L4, which is the X, plus 3 and plus 2, yep, that should work. So if it's both not 0 and not 12, then that implies that there's a piece there, which means that it's game over for us. And we can test this. So ready? Let's zoom in a little bit and see if the game over works. And then I will consider myself to have played the official entire game of Tetris here. And we can actually play a game. Well, it doesn't speed up, but I'm trying to zoom in so that you guys can see. There we go. Well, are the pieces... Oh, the pieces are showing up too low. Game over! Woohoo! Game over! Nice. There's one thing I want to do before we finish. I know this is like probably a super long video, but it's okay. We can deal with it. It's fine. One thing I want to do is I want to move all the pieces up 1, basically, because y is 13 tall, if I'm not mistaken, right? And for some reason the pieces, well, hold on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this should be piece 12 here, because this should be piece 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if 11 and 12 are there, then what I don't understand is why are the pieces... The pieces are... I guess the pieces are showing up... Okay, so the problem with the pieces is that they're actually not... I only have 4 minutes left because I'm running out of data. But the reason is I think they're moving down before they're drawn. And that's a very bad thing. That's a bad thing to just realize now. The pieces are showing up there. But they are not... They're not... Okay. So I'm gonna break the I'm gonna break what I said earlier just because we're almost out of time, and out of desperation, I want to try this. So I'm going to draw. I'm literally going to draw the pieces before we ever enter the thing. I entered that in the wrong spot. Here we go. So this is like the fastest. This is the fastest ever that I'm gonna try to do this. But we're gonna draw. We're gonna do a line on these, and we're gonna do L5. Well, we're doing X then Y, so L4 of A, L5 of A, and do I have C figured out, right? Yeah, C's figured out, so I only have 2 minutes. So L4 of A plus O, and then L5 of A, C, L4 of A plus O, L5 of A, L4 of A plus O, L5 of A plus O, C, L4 of A plus O, L5 A plus O, L4 of A, L5 A plus O, C, and then L4 A, L5 A plus O, and then L4 of A, and then L5 of A, C. Okay, I'm out of time. It's going to like stop playing or stop recording, which is frustrating, but this should work. When I get a new piece, it should draw at the very top. Yes, it did it. Okay, there we go. So then even when we die and get a game over, we will see the new piece overwriting over the old piece. That should work. And there we go. Finally. Okay, sorry, I had to delete a couple more videos, and I have 3 more minutes. And I actually coded something without showing you guys directly, but I had to calibrate it, and you'll see what I'm talking about when I show it to you. But yeah, the numbers you need to worry about here are the numbers 35 and 90. And just take a note at where I place this right here, and that I'm placing text instead of display. So yeah, let's see what that looks like. So here we go. This is our final kind of look at what this what our game looks like. So let's just make the most of it. So let's just display all the functionality one more time. So we can place pieces, we can rotate them, and well, we already know we can rotate them, but I guess, I don't know why, but my camera's trying to record this in HD, I think. But yeah, let's go ahead and rotate. We can rotate clockwise like that, or anti-clockwise. So yep. There we go. And we can also have rows removed. And we can also, hopefully I don't run out of time this time, but yeah. So here's an example of a row being removed. And we can also hopefully end the game quickly. There we go. Game over! Woohoo! It works! Great. Okay. And I'm literally at 0 minutes left. So that was a good example of our final functionality. We had rotation, we had a line at the bottom being removed, and we had our